we're going to be passing the mic for questions, so just be prepared for that. Yassir Eddebbar is my co-chair here, and he will be showing the 5-minute mark. So when you have 5 minutes till the end of your 15-minute talk slot, you'll see that, and then at 1 minute, he'll stand up. So everyone yesterday was great about staying on time, so please do the same. Allow room for questions. And then without further ado, I would like to introduce John Barth from Oregon State University. And his presentation today will be widespread hypoxia off the Pacific Northwest coast of North America, the role of shelf and shelf-deep ocean exchange processes, and climate change. Thank you, John.
Great, thank you for attending, coming back from coffee, and I'd like to tell you a little bit about what we're seeing in the near-bottom waters off the Pacific Northwest coast of the United States, and I'd like to be sure to thank my co-authors that you see listed there, as well as the folks that helped gather all of this data, including my colleagues from NOAA that conducted many of the surveys that I'll be talking about. So from the rocky coast of Norway to the relatively rocky coast of Oregon, we're in the Northern California current system. So our area of interest is that area where the west wind drift splits. One goes north into the Alaska Gyre, the other one into the California current. A classical upwelling system, so we'll be talking about how subsurface waters are supplied onto the shelf, where they fuel a productive ecosystem, but also contribute to hypoxia in that region. On the right-hand side is just a satellite sea surface image from the summer. We do have seasonal upwelling and hence seasonal hypoxia. This area has very successful fisheries. There's a number of species, including the benthic Dungeness crab, our most valuable fishery. And I list salmon on there that you may think that not so affected by oxygen, but in fact they can be, especially when that hypoxia reaches high into the water column. On the right-hand side is a satellite chlorophyll image, just showing the region of interest from the Columbia River up to the Strait of Juan de Fuca. Seattle's here. Oregon State University is further down there in Oregon. So just to get the idea here, we're upwelling water from the very top of the OMZ, probably around 200 meters or so. There is a current called the California undercurrent going poleward. We heard a little bit about that yesterday, about how the Pacific equatorial water can reach up to this area at about 20% of the influence. The shelf processes are very important, the respiration of the chlorophyll blooms with that material falling to the bottom. And we're seeing hypoxia reach right next to shore. So here we are on our research vessel. You can almost throw a stone to land, and the crabbers are working just inshore of that, perhaps exploiting the refugia of the high oxygen right near the shore. So the idea here was to amass all the observations we could for one particular summer and really map well the area of hypoxia or low oxygen. So we're going to have lots of ship-based surveys. We've got some sensors on the groundfish surveys conducted from charters. We've got students learning the techniques of measuring oxygen in situ. And then lastly, the autonomous vehicles now that we use, the underwater gliders that sense oxygen with an optode. So here is that study area again. This time this is Cape Blanco, the Oregon-California borders here, Columbia River, Strait of Juan de Fuca. And I've just color-coded all the observations by who conducted them. We've got the International Pacific Halibut Commission sending out a boat to do a survey every year from which they base the models for the halibut and what the catch might be. So there's going to be this connection to the fishery surveys where you really need to understand the hypoxia spatial distribution to understand, of course, the fishery surveys. We've got these couple of gliders down here, some work we've done off the Washington Shelf and some work off Central Oregon. And I mentioned there's about 800 vertical profiles from the fishery surveys. There's over 10,000 profiles from the gliders. So order of magnitude more of sampling. So if we look at the distribution in time, over here on the left-hand side, we define the upwelling season as starting sometime in March or April and going through the northern hemisphere fall. And we're lucky to have the gliders out nearly continuously in some cases, so we get the early season conditions, and then the survey vessels come out and fill in the gap even better. So let's look at some of the data. These are just color-coded again by the surveys. You can see a wide range, and I'll be using 60 micromoles per kilogram as that hypoxia, equivalent to roughly to 2 milliliters per liter. Or excuse me, 2 milligrams per liter, 1.4 milliliters per liter. And another remarkable thing is how early our upwelling season started this year. So a high pressure ridge in the North Pacific started the upwelling early, and it lasted very long. And you can see us getting into the hypoxia region for very much of that season. All right, so the payoff is this map. So what I've got color-coded is the oxygen content of micromoles per kilogram, and this number 60 is the border here between the light blue and everything else. So quite a detailed map because we do have the survey there. So we've used a spline fitting technique to just map it for the whole season, essentially. And what emerges are a bunch of interesting patterns, in particular these mid-shelf lows, this ribbon of low oxygen water. So quite widespread. It's 50, 60, 70% of the shelf, depending on how you define it. It's about 15,500 square kilometers. And I checked that real quick against the Baltic, so it's about the third of the size of the Baltic. It's on par with the hypoxic zone off the Mississippi River in the United States. So pretty good size. It extends, as I mentioned, up into the water column, sometimes as high as half of the water column. So let's just look a little bit at these patterns. There's low dissolved oxygen in several places, off the central Washington shelf, which is quite a wide shelf, in an area influenced by Columbia River, and down near a submarine bank. And I'm going to explain each of those mechanisms in just a moment. There are normoxic or high dissolved oxygen areas, of course, near the shore. That's that refugia I mentioned. We get south of the Strait of Juan de Fuca, where the tidal velocities are quite large. And lastly, we don't really see hypoxia south of the Cape here, where the continental shelf narrows. All right, so let's look a little bit more into these guys. I mentioned the retentive shelf, so wider area, more respiration, less exchange of the water, the river plume facilitation, and lastly, a flow topography interaction. So I mentioned some of those. So let me talk about some of these physical mechanisms that lead to this pattern. So we've got a submarine bank, the flow comes down, roaring down the shelf. It has to go around that obstacle, and it leaves a quiescent area inshore, which is a perfect incubator for phytoplankton blooms. That drops the material down, it's not flushed as efficiently, and we get that low oxygen zone on the shelf. Another type of mechanism is at the base of a river plume, where you're not, in our case, we're not supplying the nutrients by the river plume. It's actually low nutrient, but that mixing pulls up the nutrients from the ambient coastal upwelled water. That's what drives the productivity. So in a sense, it's a hose mixing up those nutrients in that area underneath becomes more hypoxic. All right, so I wanted to talk a little bit more about this idea that from this morning's plenary, where it's low-cost sensing and trying to get the fishing fleets and citizen scientists involved. So what we've done is build a relatively low-cost, easy-to-deploy system based on the oxygen optode technology. We partnered with the Sexton Corporation for the packaging, In Situ, of course, for the optode, and Lowell instruments for the data connectivity. So you can see the sensor there. It's relatively small. You can see it in the crab pot here. And this is a great set of Dungeness crab coming ashore after a soak for a couple days. As it comes onto the deck, it Bluetooths over to a deck hub that's here, and subsequently cell phone to shore. So we get the data more or less in real time. So we partnered, as an example, in that same summer, 2021, with about 8 or 10 fishers up and down the coast. And you can see the array there. And the idea is that, the research vessels can be out there for maybe one survey, but during the fishing season, the fisher partners are out there the whole time. So we can start to amass a data set from that looks something like this. So on the web, we post the locations and the time series from a particular 2 or 3 day soak. You can see the temperature in red and the dissolved oxygen in blue. And this particular one is in a hypoxic area. We want the fishermen to know as they lower their pots whether it's hypoxic or not, because why waste the time and capture crabs that are going to die? In fact, in 2002, that's how we were tipped off to this area being a problem, is the fishermen were pulling up pots full of dead crabs from the hypoxia that set in after the crabs entered the pots. So we're working on a system to amass all this and make sense of it. You can see the various records from that particular year. Okay, so what about changes over time? This is a pretty dramatic set of maps. I showed you this one on the right already. If you go back to the NODC archives, the World Ocean Database, this is from the 1950s through the 80s. This is the period from the groundfish surveys from NOAA, 2009 to 2018. It's the same color scale. And what your eyes might see is the patterns are robust because of the physics that I explained, but it's pretty obvious that there's a decline. And that decline is, 7 times as big as Laura mentioned this morning for the open ocean. It's something like 7 micromoles per kilogram per decade. So we're seeing some real changes up on the coast. And it's a combination of source water, that long upwelling wind period, which we think is also influenced by climate change, and lastly, that respiration and retention. So I'll just put my summary up here. We're looking forward to more low-cost arrays of sensors out on the coast. We have a project now looking at next steps to do multi-stressors. So PH, who's meeting in the other room, and I said that that's 2 sides of the same coin, as well as harmful algal blooms and marine heat waves. So I hope to speak with you about that next time. Thanks for your attention.
We're going to pass around the microphone, so if you have any questions, raise your hand, please.
Excellent. Thanks a lot. Very exciting. What is the biofouling problem? Is it a problem, or you mentioned 12 weeks? It's surprisingly long to me that you can have these sensors out there in shallow waters. And is there some possibility to expand that to other regions of the world ocean, of the global coastal ocean, and how could we do that?
Yeah, absolutely. So the sensors, a typical crab pot deployment is only days, 2 to 5 days kind of thing. So they do get them back. And we've been doing the calibrations in our laboratory. So we used to say that it's a Netflix model, but nobody knows what that means anymore. Where we actually calibrate the sensor, send it to the fishermen. They deploy it and send it back. And yes, we would love to expand it to other areas.
Thank you very much, Jack.
If you have any other questions, we have a coffee session after our lunch. Please reach out to Jack.
Thank you very much, Luba. The next presenter is Yassir Eddebbar from the Scripps Institution of Oceanography, and his talk is on sources and variability of oxygen supply in the upper equatorial Pacific, insights from high-resolution models.
Thank you. And this is actually a good segue from the last talk and from Laura's question. What can we learn from high-resolution models on upper ocean oxygen variability and supply routes? So I'm going to pick up where we left off in the discussion yesterday, where we know that there's some discrepancies between observations and models, although I got to say I might need to revise this slide after Laura's talk this morning. Maybe the models do agree if you look at oxygen space or an isopycnal space, but I would also argue that even if they did agree, the models don't represent the oxygen minimum zones well in that region. So we shouldn't necessarily trust their projections, even if they agree in that region. And I would say another major gap that's becoming clear is that we don't fully understand the processes governing oxygen distribution in this region well. We know that, for example, in the eastern, central, and eastern equatorial Pacific, we know that the equatorial current system, namely the equatorial undercurrent and the Tsuchiya jets, bring oxygen back to the eastern Pacific. But there are other processes. This is a highly turbulent region. There's a lot of eddies, and there's eddy activity along the equator, just north of the equator. And we see some of the highest eddy kinetic energy in the world's ocean along this region. There's eddies essentially propagating away from eastern boundary upwelling systems like anticyclonic mode water eddies that spin off low oxygen waters out into the pelagic zone, and coastal eddies that tend to ventilate the OMZs. So eddies might be quite important in representing, modulating the OMZ regions. And then turbulent mixing, this is zonal velocity along 125 west. The equatorial undercurrent is essentially shearing against the south equatorial current. So there's a lot of turbulence, a lot of mixing that's happening in the upper ocean. So one would actually perhaps expect a relationship between stratification and oxygen because of the impacts of mixing here. So a couple questions that I want to touch on today. I'll mostly talk about the first one, what processes balance oxygen consumption in the upper equatorial Pacific. This is where a lot of the tuna fisheries essentially feed and travel along the equator. So we want to know what drives the oxygen supply in that region, and how do these processes influence the seasonal to interannual variability of oxygen. So for the methods we use to get at the role of eddies and mixing, I use an eddy resolving configuration of CSM. This is a global Earth system model that's run at 1/10 of a degree. So it's highly computationally expensive. And we run it for 5 years using an annual core forced atmospheric data set that essentially reproduces the annual cycle, so we can understand questions about the seasonal cycle and mean state. And we just finished a 60-year hindcast with the GRA reanalysis that allows us to look at interannual variability and so phenomena. And one of the key things that's coming out from the 1/10 of a degree compared to like a CMEP type configuration is that we see a more extended OMZ towards the west, a more oxygenated equatorial oxygenated tongue, and a lot of that is associated with a better representation of the equatorial current system. So the Tsuchiya jets, that north and south subsurface countercurrents, emerge at the 1/10 of a degree, and you don't see that as clearly on the 1 degree configuration. So we have a slightly more realistic equatorial current system representation. And then the EUC is also less tilted upwards. There's a paper by Julius Busecki with the GFDL model a few years back that shows essentially a similar effect where the EUC is flatter, and so it brings more oxygen deeper into the eastern equatorial Pacific. So we have slightly more realistic depth. So there's some really nice potential there for high-resolution models. And back to the discussion yesterday, perhaps we can look at different high-resolution models and how they represent the OMZs at this resolution, and that can inform next steps for CMIP models. So then the first question, which is what processes balances oxygen consumption in the upper equatorial Pacific thermocline. We got the jets. We also have quite a lot of mixing that we know exists along the equator. We have eddies. So we decompose the oxygen budget in the mean state and look at the role of mean advection. This is upwelling and zonal advection and divergence and all that. And then we have the eddy term, which we use a Reynolds decomposition to isolate and look at the role of vertical mixing and sources and sinks. So what do we have? So the first slide here just shows the contribution of the mean advection. This is essentially the mean flow by the zonal and meridional and vertical advection. We have pretty strong contributions from eddies right along the passage of tropical stability vortices. So there's some balance there between the mean flow and the eddy flow, and really surprising contribution of mixing. So that was one of the more interesting results from this budget balance that compensates for the negative contribution of consumption in the eastern to central equatorial Pacific. So let's take a look at a few of these terms. The mean advection, this is not new. So this is essentially the contribution, the equatorial undercurrent, bringing a lot of oxygen to the eastern Pacific, as well as the Tsuchiya jets, the north and south subsurface countercurrent and the north equatorial countercurrent. Upwelling essentially is responsible for the advection of low oxygen waters to the upper ocean. And just a slight digression here, we note that even though the equatorial undercurrent has a huge transport towards the eastern Pacific, the Tsuchiya jets, for example here, the northern subsurface countercurrent is quite efficient at reaching the OMZ volume. So even though it's weaker transport, it can be pretty important for ventilating the actual OMZs because of its isopycnal depth space. The interesting results here are that eddy advection and mixing are important. I don't have time to go into the mechanisms in detail, but this positive contribution to the tendency is the result of a bunch of different processes, namely eddy trapping and eddy steering of the intense lateral gradients of oxygen that are set by the EUC and other jets along this region, but also eddy pumping as the eddies are propagating towards the west, and subduction along the leading edge of these eddies leads to pretty strong advection of oxygen to depth. And then finally, vertical mixing is really important and is also tied to the propagation of tropical stability waves. So as these vortices travel towards the west, they modulate the shear, and that impacts turbulence. And you could see that in the air-sea flux of oxygen and surface AOU in this model. So I want to end with a couple questions. The final question, which is how do these processes impact the seasonal to interannual variability? The decrease and increase of oxygen with seasons from winter to summer is actually not just an mean advection contribution. There's strong contributions from eddies, and mixing, and that's tightly associated with eddy kinetic energy. Whereas we don't see that much seasonality in the model for biological activity. So a substantial contribution of seasonal variability is associated with eddies and mixing. And then the ENSO variability as well is also tied to this net balance of large opposing fluxes. And we see that, again, mixing is substantially reduced during, for example, the El Nino of 97, 98, where the EUC essentially slows down. So we get reduced supply of oxygen towards the Eastern Pacific. We get reduced upwelling, and also there's substantial heave or deepening of the isopycnals. But the mixing term is quite large. So a key message here is that mixing is actually quite important in the upper equatorial Pacific. So that's the main questions. I want to leave enough time for questions for the rest of the talk. But I just want to reiterate some of the main conclusions. Higher resolution has an impact on the OMZ distribution, mainly through improved representation of the equatorial undercurrent. We see this in a different model, as well as the emergence of the Tsuchiya jets. And also they're resolving eddies, and eddies have essentially a rectified effect by also impacting mixing. Eddies and mixing are important in the mean state, as well as potentially seasonal and interannual variability, whereas advection tends to be the dominant term deeper in the thermocline below 200 meters. And so I think in the future, as we deploy more biogeochemical Argo floats and deploy new measurements, it's important that we keep this high variance in mind as we observed this region and as we constrain the oxygen balance here. And I'll take questions.
Great, we have 2 minutes for questions, so thank you, Yassir.
Hi, sir. Thank you very much for the talk. You mentioned about the role of ENSO in modulating this oxygen. If you look at so in CMIP6 base model, you see that the ENSO is not well reproduced. I mean, it's not correctly reproduced in many of the standards. And then you go these high resolutions. Have you checked how the ENSO looks and whether the representations on the oxygens comparable with the observations?
Yeah, so I haven't actually checked the internal dynamics, so anything below the surface, how the thermocline does with ENSO. With the sea surface, it actually does really well. So that was a hindcast simulation forced by the atmosphere. So we expect it to do pretty well in terms of ENSO variability as opposed to a fully coupled model. But in terms of the ocean response, yeah, that would be something really important to check, just how the Kelvin waves are propagating and how the thermocline is responding. I would, as Laura mentioned yesterday during the talk, during the discussion, we use these models to gain an idea of the mechanistic response with what we know, as opposed to try to identify exactly what happens in nature, which is what observations are for. Yeah, so, and with the CSM model, 1/10 of a degree, there is better representation of thermocline depth in the mean state. There's a paper by Small et al. That shows better representation of ENSO, yeah.
Thank you very much, Yassir. Now we're going to move on to our next speaker. Andreas and Yassir can continue to discuss over lunch. So our next speaker is Dimitri Gutiérrez from Amarpe, and his talk is on drivers of regional deoxygenation periods in the northern Humboldt Current system during the late 19th century. Thank you, Dimitri.
Thank you. Good morning. Well, our work is has a different focus, a different approach. We work with sediment records collected from the central coast of Peru within the oxygen minimum zone just in front of there. And this OMZ as has already been described, can be very shallow and very thick, and it is strongly modulated by the equatorial circulation. First, in order to interpret these records, we have to remind a little bit about the seasonal and interannual variability of productivity and the oxycline. Here, you can see the climatology of chlorophyll A, winds, and insolation for the Peruvian coastal band. And it is clear that there is an annual cycle, even though the winds are always favorable to upwelling, they display a seasonality. So they are stronger during spring and weaker during summer, but the productivity peaks during summer and not in spring. So that means that the light limitation is critical for the productivity in the coastal waters of Peru. But in terms of the oxycline depth, it has a semi-annual signature. The oxycline shoals during spring related with a stronger upwelling, but also shoals during summer when the productivity is higher and the respiration in the water column is stronger. Now, moving to the interannual time scales, here we are comparing the SST anomalies in the region El Niño 1+2 versus the chlorophyll A anomalies from satellite from 2000 to 2015. This is the nearshore band, this is the offshore band. In both cases, you see a negative relationship, but the amount of variance that is explained is only 21 to 22%. But if we extract only the summers of this period, the amount of variance that is explained is over 50%, and you have a much more clear relationship. So we can summarize this that during the austral summers of La Niña, the Peruvian waters are significantly more productive than during El Niño or during neutral conditions. Now, in terms of the interannual variability of the oxycline, here, for example, we have a time series in an onshore station at central Peru showing the oxygen anomalies and the depth of the oxycline with time. And it is clear here that during El Niño, you have the deepening of the oxycline, positive anomalies in the water column, and in the opposite during La Niña. And this is not only a coastal phenomenon, because if we compare, for example, the 2000 La Niña versus 1997 El Niño, you can observe a clear difference in the depth of the upper boundary of the oxygen minimum zone. So our records come from the central Peruvian area in the continental margin. In the Pisco area, we have collected a number of cores in the last 15 to 20 years. In addition of this area, there are some published records from Callao, which is 200 kilometers in the north, and from Mejillones Bay, which is at 23 degrees south. Most of these studies have been multi-proxy studies, and I will not describe in detail these proxies that we have studied, but we will focus more on those ones that are related with paleoproductivity and paleoxygenation. So here is a comparison of the stratigraphy of several of the cores that I showed in the map. As you see, there are several commonalities among these cores. The green layers here are the diatom-enriched bands. In geological terms, they could be described as diatom oozes. They are very conspicuous by eye, and they also exhibit a very low density in terms of sediment density. And they all occur above this sedimentological shift that has been previously dated at about 1850 AD. So, for example, in the core B14, which has been one of the best studied, yes, the top diatom band is dated at about 1885 to 1890. We have conducted independent chronologies in other cores, And we have a very high degree of coincidence, indicating that these diatom bands were deposited between 8060, 8065 to 8090. In Chile, in Mejillones Bay, there have been reports showing a thick diatom band dated at about 8070, which is in the same time range of the other diatom bands observed in the Peruvian sediment cores. Okay, so if we look at the time series of these proxies, the amount or percentage of biogenic silica and dry bulk density further confirms the existence of these diatom-enriched layers. But most important than that is, or more important than that, is that within these diatom-rich layers, we get very high values of delta L15 in organic matter and very high values of molybdenum enrichment. That means that there was a complete utilization of nitrate and denitrification in the water column. This occurs with oxygen depletion in the water column, but also it implies the occurrence of sulfidic conditions in the seafloor. Given the values that we observe that are the higher ones or the highest ones as compared with, for example, all the Holocene records that we have studied, we infer that these were very strong oxygen depletion events and that the anoxic conditions could have reached even the subsurface waters. And all of this took place in a period in the late 19th century where the alkanon-derived SSTs show a kind of concavity within this high temperature period. And also peaks and lows indicating that the conditions were varying during these sedimentation periods. About the composition of the diatoms in these diatom-rich layers, we conducted a PCA on the diatom composition. And we arrived at the principal component 1 is related with a high abundance of coastal species. I mean, coastal upwelling species, like all of these ones that are listed here. And the principal component 2 is related with the presence of subtropical warmer water species. So as you can see in the top panel, it is clear that these diatom-rich bands were mainly formed by these coastal upwelling diatom species. Furthermore, by looking at other components of the ecosystem, we also checked the abundances of fish scales in the same time period. Actually, this is from a paper published by Renato Salvatecci. I didn't put his name here. And in summary, the local fish biomass was impoverished during this period, and mainly because diminution of the concentration of anchovy fish scales. There was a slight increase of warm water species, but in terms of total numbers of fish scales, this is very low. So what would be the explanation of what we have observed in the proxies, the climatic context within these deoxygenation periods occurred? We have explored the Hadley SST reanalysis for the whole period from 1854 to 2021. And these patterns arrive. The first one is related with El Niño. The second and third ones probably related with Modoki, El Niño, or Modoki La Niñas. But if we do the same for the 1860, 1890 period, there are some differences. For example, the first AOF is more biased towards the Eastern Pacific, and the second and third, especially the third EOF, shows regional variability here, where you have an opposition between the SSTA anomalies in Central America and Colombia versus the Peruvian and northern Chilean coast, a feature that does not appear when we look at all the data. So we extracted the time series from this 1860, 1890 period. In the first case, the first EOF, it is clear that it records the very strong and well-documented El Niños of 1877 and 1888, 1889. But with the exception of those periods, in general, it seems that there was very low amplitude of ENSO in this period. But in the other EOFs, we have very frequent variability between positive and negative SSTs, and indicating that there were frequent regional warming and cold events. So this leads us to further explore the comparison between what is happening in the El Niño 3.4 versus what is happening in the El Niño 1+2 and in the coastal band between Peru and northern Chile. And this pink area is the period of interest. And as you can see, there is a lot of things occurring here, a lot of variability that is not related with the Central Pacific, especially in the first 20 years. We computed the gradient, the thermal gradient between the SSTA gradient, actually, between the offshore and onshore SSTAs. And we interpret this cross-shore SSTA gradient as a measure of the degree of strength of upwelling. So positive values should correspond to stronger upwelling and negative values to relaxed upwelling. It is clear that in this period you have a higher amplitude of this index, and this can be quantified as well, and especially in summer, the difference is much more significant. So, this is a summary and also the proposed mechanism that we are developing. We hypothesize, given all of this evidence, that the mechanism that drove these, that had driven these deoxygenation events was the rapid alternation between upwelling activation and upwelling relaxation, which had enabled blooming of coastal diatoms, followed by massive sedimentation, strong oxygen depletion in the water column, and development of anoxia in the bottom. I will further say that we have not observed or recorded this kind of events in the observational period in the last 40, 50, or 60 years. But in the coastal embayments, we frequently observe during summers that after the upwelling advection of oxygen-poor waters and development of stratification because of sunlight during summer, there is a lot of these blooms and then anoxia in the seafloor. But in that case, the forming species of these blooms are dinoflagellates, not diatoms. So now we are starting to look at the dinocysts and biomarkers of dinoflagellates in the sediment cores in order to further study these events. Thank you.
One question.
Hi, thank you. I was wondering, when I was looking at your time series in the 60s, it seems very opposed to so the diatom PC were very low, both of them. You had more fish. I mean, it seemed like really the opposed version of those events. And I was wondering if you tried to maybe compare to another, where you would have maybe more data.
Yeah.
That would be a counterpoint, maybe to your...
I didn't put much into detail that latest part, but there have been publications about that. Well, yes. If you look at the species level, there were alternations of the dominant diatom species in the 20th century. For example, in the first half that you were referring, there was a higher dominance of one of the Thalassionemas, which seems to be more related with probably frontal waters. And then for the past 50 years, there is another Thalassionema which has been described as a dominant species in wintertime, so that is the time where upwelling is much more active, and this coincides with the coastal cooling that we have observed during from these proxy records. So there is a kind of consistency in the diatom composition as related with other proxies for SST and things like that.
Okay, so I think next we have Nguyen looking at a different region, the Northwest Atlantic Shelf and Atlantic Basin. And I think, wow, this is a recorded talk. My apologies. So he'll be presenting, or she'll be presenting on temporal trends and causes of deoxygenation, a comparison of Northwest Atlantic Shelf and Atlantic Basin.
Hi everyone, my name is Hang from University of Connecticut. Today I'm going to present to you my research on temporal trends and causes of deoxygenations in the Northwest Atlantic Shelf. First, I want to give you some background about my research. My research is about oxygen, an important element for organisms and geochemical cycles. The global dissolved oxygen has declined by more than 2% since 1960, which is shown in the right panel, and is predicted to decrease by another 1 to 7% in the next 100 years. These changes are attributed to global warming, enhanced stratifications, and biological consumptions. The dissolved oxygen trend and ocean warming happen at different rates among the globe, which is shown by the spatial variability of these two changes here. Now we want to know what is happening in our Northwest Atlantic. As we zoom into the Northwest Atlantic, here I'm showing the sea surface temperature in the last 30 years in the Northwest Atlantic. And the sea surface temperature in the regions has increased by 0.37 Celsius per decade in the last 30 years. This is one of the fastest ocean warming. Some of the warming trends are associated to the changes in water mass. And what do I mean by change in water mass? In the regions, we already have lateral currents, which is shown in the blue arrow on the right panel. And in offshore, we have the Gulf Stream flowing northward. And in recent years, there has been evidence that the Gulf Stream is migrating northward, competes with the lateral current, and this changes the water mass in the region. So these changes indicate that there should be some change to the oxygens. And indeed, we have some oxygen declines already acknowledged in the Atlantic basins. However, the observation in the shelf are insufficient and don't match with the time scale of a temperature trend. So for the first question, we want to establish the oxygen trend in the shelf and compare that with the one in the basins. Then we want to find what is driving that trend because we have increased sea surface temperature, which drive decreased oxygen solubility, as well as biological activities and change in water mass. Which one of these are driving the oxygen trend? To answer those questions, we will use World Ocean Database, which is shown on the right panel with the sampling locations. The sampling locations have a good coverage for the regions, which give us some confidence to approach this project. We will use the data from 50 to 100 meters after we consider the mixed layer depth in the region. For the first question, we will use the annual average and estimate the linear trend. Before we use the we estimate the linear trend, we use the number of observations to identify the time period that we can put the linear regression on. And after that, we estimate p-value to assess whether the trend is statistically significant or not. For the second question, we estimate oxygen solubility as a function of temperature and salinity, as well as other parameters. We also estimate AOU, defined by the difference between oxygen solubility and the observed oxygens. If AOU is positive, it means that the observed oxygen is lower than what it should be, which means that there should be other processes that consume oxygen, including respiration, stratifications, or changes in water mass. So AOU can be used as a tracer for these processes. Now here's our result. Here I'm showing you the red bar indicates the number of oceans measurements from 50 to 100 meters. The blue plot indicates the annual average oceans in that depth with 95% confidence interval. From the number of measurements, we decide to focus on the time period from 1988 to 2019 because this time period has a continuous long record. At this time period, the ocean trend declined by 1.386 micromole per kilogram per year, and this change is statistically significant due to the p-value. Now, we put this trend in the shelf to compare with the already known deoxygenation in the Atlantic basins. And as we compare those two changes, we conclude that the deoxygenation in the shelf is much greater than the trend in the Atlantic basins. So what is driving that significant trend? Before we can find the trend for the contributors or identify the contributors, the one challenge that we need to address. So one criteria for the time series is that it has to be long, frequent, record, continuous, and uniform. However, this is not always the case. Here I'm showing the percentage of data contributions from 6 subregions in the regions, and we noticed that after 2010, the Canadian side terminated their record. Meanwhile, the US side significantly increased the number of measurements. So we have to look at the time period that arguably all these subregions are uniformly distributed. And we choose the time period from 1995 to 2010 for this criteria. At this long time period, we estimate ocean change along with AOU and ocean salubility change. And at the end, I'm showing the functions to show how the AOU change adding up with the solubility change to conserve the ocean chain. And by comparing the AOU column with the solubility column on the right, we find that the magnitude of the AOU change is much greater than the one from the ocean solubility, which indicate that at all these regions, subregions, the AOU is the important contributor to the ocean trend. Another way to look at this is look at the trend through time. Here I'm showing you the percentage contribution of AOU and solubility change to the ocean change. The AOU change is shown in the blue portion. The solubility is the orange portion. So throughout the time, for most of the time, AOU is determined to be the most important driver, which is shown by the dominant of the blue portion. We also notice at some time period, for example, marking in the red box here at 1998, 2012, and 2015, these are the marine heatwave events. So is it expected that solubility should dominate the ocean trend? As AOU is an important contributor to the ocean trend, so we want to go one step further to explain what is driving that AOU. In principle, we have 3 possible change. We can have change in stratification, change in water mass from low to high AOU, or change in biological activity, such as marine productivity. So which one of these can explain the AOU signal? For stratifications, we compare the correlation between the AOU change, which is the blue plot, and the stratification index n square, which is the red plot. We notice that at some time period, the R square is high. For example, at 2009 and from 2009 to 2019, This shows that at time period, the stratification has a good correlations with the AOU change. Another factor is the change in the water mass. So we found the AOU contain of lateral currents around 50. Meanwhile, the AOU of the Gulf Stream is 150. So when Gulf Stream compete and replace with lateral current, AOU is expected to increase. The last factor is primary productivity. The primary productivity in the regions has been decreasing, which means that the organic flux for respiration decrease, which means that the amount of oxygen required for that respiration should also decrease, which means decrease AOU, which is inconsistent with the AOU that we find in our study. So more research should focus on this aspect. In conclusions, we found that the oxygen trend from 50 to 100 meters of the Northwest Atlantic Shelf decreased by 1.386 micromole per kilogram per year from 1988 to 2019. This rate is much greater than the rates we found in the basins. AOU is an important contributor to this trend, and which is consistent with the change of water mass and stratification in the region. AOU change can also be caused by other processes such as the organic matter cycling or benthic pelagic feedbacks, so more work should focus on understanding and projecting these changes. And thank you so much for your listening.
Please email Hung directly, and we actually have a couple minutes. Should we go straight to the next speaker, or are there any questions to our previous speakers? Yeah.
I have a question for you. I can talk loud. No, it's just over online. Yeah.
It was really good, really nice work. I have a little bit of a sideways question, right? So CSM has really big bias in oxygen. Is this look any better in CSM2 at high resolution with the JRA forcing? Has there been any improvement? And then what does that mean for like Jack's location? You know? Jack Barth. He's talking about the upwelling, right?
CSM2 did worse than CSM1 with oxygen in the low resolution model, so we went in the wrong direction, but it had to do with ventilation in the North Pacific. So at higher resolution, that's, we can look at the impact of just improved resolution, irrespective of configuration, and there is improvement in some aspects of the OMZs, but the large scale distributions are still problematic, and I think they have to do more with the coupling of the ocean and the atmosphere and larger scale circulation than necessarily eddies or the jets. But when you look at local regional regions, that's where you get improvements, because you have the ocean is turbulent and is not laminar. Yeah. Sure. All right, Lisa.
Taking questions for any speaker? Sure. Yeah. Okay, so I had a question for Jack, actually. Just, it seems like there was some kind of state change 20 years ago off Oregon, where all of a sudden you started seeing this inshore hypoxia. Is that right? Or did you just, you would have detected it before from crab kills, right? So what caused that? Is there a tipping point? Something caused the whole system to change?
Yeah, Lisa, I think you're referring to when we first noticed from the fishermen the dead crabs in the pots. That was there's interannual variability, of course, and that was a particular year where there was a low oxygen event that drove it below, as you say, a tipping point. But the trend has been true since the 60s. So,
sort of linear.
Yeah, exactly. And the key point is that the shelves are well ventilated, right? They can be. as the winds flip back and forth. So as we get more persistent winds with climate change, things can be held up there and essentially cook for longer. So I think that's a bit of what we're seeing.
But you were having hypoxic events in the 60s in the inner shelf?
No, not until starting in the 2000s, as you pointed out.
So is that a product of secular climate change? I mean,
yeah, what I'm saying is that things flip back and forth, and you put the trend on top of that, so the lows go into the hypoxic zone.
All right. So if you have any other questions, please save them till lunchtime. Our next speaker is Paulo Coelho. I'm really looking forward to this talk. He'll be discussing the impacts of deep water jets on the Atlantic oxygen minimum zone, so we're moving further south. Go ahead, Paulo.
Thank you. Good morning. Thanks for staying until the last talk of the session. And this talk is actually in line with Yassir's talk early on, which is about the impact of high-resolution processes on the emergence of zonal jets, which seem to be important in the supply of oxygen to the OMZs, or at least the edge of the OMZs, particularly in the North Atlantic Ocean. What I will present here mostly published recently in a publication in early February. So we know that observations show decline in oxygen concentrations. This is probably due to anthropogenic effects. Models show some disagreement in terms of long-term projections. And however, models are tools that are needed for not only for projections of climate change or the anthropogenic effects, but are also needed for diagnosis studies. But one condition for models to be used for these diagnostic studies, that they at least provide a realistic representation of the oxygen fields. And one of the things that I did, what motivated me to do this study is that the low resolution 10-kilometer regional run that I had didn't provide a realistic representation of the OMZs in the Atlantic Ocean. So I increased the resolution. And I did this on a climatological sense. This is merely a comparison of two basin scale model simulations at different resolutions. One is 10-kilometer resolution, which is nowadays the limit of climate models, and one at 3-kilometer resolution. So we increased a little bit the resolution of the models and see what happened. And I basically started this, it's a repeated 2003, and I used 2003 because it's a neutral year in terms of the Atlantic Meridional Oscillation, the other North Atlantic Oscillation. So it was a neutral year, so I used this as a kind of a test year for the model simulation. So after a spin-up of 9 years, starting from SODA conditions, I will show here 7-year averages of model runs. And I'll go straight to the chase here. I use cars as the model of the truth. I know climatologists are full of problems, but I use cars to compare with the 10-kilometer run and the 3-kilometer run. And immediately we see in the, I'll call the 10-kilometer low resolution, we see that there is a strong excursions to the west of the low oxygen, and these are 3 different depths: 250 meters, 450 meters, and 650 meters. 450 meters is more or less the core of the OMZ in the North Atlantic, in the North and South Atlantic. And you can see here that, well, a few things that are important to notice. First, the strong westward excursions, probably due to the surface equatorial jets here, westward. And also at 650 meters, we don't see any sign of the OMZ. This black line is the 80 micromole per kilogram isoline, which I use as the limit of the OMZ in this case. And you see that it doesn't exist here anymore. We still see a sign here in the high resolution run. This expansion is more well behaved in the 3-kilometer run, so that seems to be an improvement in this sense. And another thing that is important, if you look at these high oxygen regions here in the low resolution one, they're not present neither in the climatology and also not in the 3 kilometer run, which might be an indication that adding processes at depth may be important for the redistribution of these low oxygen concentrations across the basin. And it's important to mention here, because if you do a Taylor diagram, and I did all this in the paper, if you do a Taylor diagram of this or target diagram of whatever, you're good. You'll be satisfied. If you don't look in the details of the simulation, although you see that it's clearly wrong, the Taylor diagrams are acceptable. So one would be happy with the simulation if you don't look into the details. Okay, so we go into the velocity fields, and what's the main difference between the two runs? So again, I have the black line here is the 80 micromole per kilogram, and the main difference is that, okay, the westward jets are more or less well reproduced in both simulations, but you have the emergence of these eastward jets at 250 meters, but particularly at 450 meters. You see these zonal jets more or less at the Rhine scale, and I want to get into the dynamics of zonal jets. It's a complicated problem in itself. But it seems that there are two things that you need to reproduce the zonal jets, the basin scale and high resolution, because the zonal jets emerge as a transfer of energy across the scales of motion. And that's important because usually, and nowadays we have a sense that we need high resolution only at the surface and on the continental shelf because of the Rossby radius of deformation. So we only need to resolve these processes in those regions. What we show here is that if you actually, and these zonal jets exist, measurements in the Atlantic Ocean are reliable, and we see that the zonal jets exist. And if you don't have them, it seems that there's a big impact on the OMZ structure. So if you look in the vertical here, this is a 23 west, not 26. And I use these 26, 23, 30 because colleagues from Guillemar, they visit these lines frequently. So there is historical data to compare with. And again, we see that the 3 kilometer run shows a better representation of the North Atlantic OMZ structure here. The equatorial undercurrent structure is here. And in the upper part, between the 25.8 and 26.6 isopycnals, the simulations are more or less similar. So it means that even the low resolution run satisfactorily simulates the upper 300 meters, say. But below the 26.6, so this is the core of the OMZ, we see that the main difference is the emergence of these zonal jets. And they seem to have a big impact on the structure of the OMZ. If you remember, this is where they make the connection between the oxygen-rich western boundary and the edge of the OMZ. Another thing that the fact that the surface jets are more or less simulated in the low resolution run, but the eastward jets deeper down are not well simulated, is that you have a distortion of the OMZ. This is the hypoxic layer thickness from cars and from the high resolution model, so that's just realistic. And I think that's also in a climatological sense. I'm not talking about climate change, it's just trying to see if the model is doing a good job. And you can see here that the hypoxic layer thickness is completely distorted in the low resolution run. And one of the reasons for that, and one of the reasons why you don't see these regions, these low values here, particularly in ROMs, you have the numerical diffusivity is proportional to the grid size. So, if I remember correctly, yeah. So if you have a low resolution, you have more numerical diffusivity, so you tend to kill these zonal jets here. They're important, but as you can see here, they're really small in terms of intensity, in terms of speed. So if you have high numerical viscosity, you're going to kill these things. But one important thing, if you look only at the volume of the OMZ, although you stretch them out, the volumes are surprisingly similar, right? So you have to be careful when you look at these things, right? Oh, the volume of the OMZ was satisfactorily or correct. Well, we have to look at the structures as well. Now, when you look at the budgets, and that's also in accordance with what Yassir showed earlier, we have this balance between biology and physics, particularly in the upper ocean. And then you have, okay, when you break down the physics into advection and mixing, we see, again, the importance of mixing in supplying oxygen, particularly for the upper part of the OMZ. And then below 300 meters, advection dominates the positive supply. And this is at 26 west, the edge of the OMZ in the North Atlantic. You have this more or less negative or more positive values here associated with the location of the jets, between 400 and 700 meters. If you do a box average at the core of the Etna, the Eastern Tropical North Atlantic region, this is the balance in the low resolution run and in the high resolution run in the vertical. Basically, you see this kind of a Martin curve below 200 meters. Well, yeah, the upper 200 meters, you see this balance between physics and biology. And then the mixing term here also relatively important at the top because you have a strong oxycline in that region. But the main thing here, and what dominates the physical terms, is advection below 200 meters. Mixing, somewhat important, but very small. And also we're looking at very tiny values here. But again, you have a stronger advection in the high resolution run. When we try to explain, in trying to explain the asymmetry between these jets, one possible explanation is the fact that usually this is the isopycnal potential vorticity between, in the upper layer, 25.8 and 26.6. And you can see that usually the westward jets are associated with more widespread isopycnic potential vorticity lines, and which are indicative of more homogeneous conditions. So these jets are usually associated with homogenized pools of tracers, as opposed to the westward jets, which are associated with regions of intense potential vorticity gradients. And given that they're more representative, they're more well represented in the high resolution run, I think that's why we see this asymmetry. In the upper layer, they're more or less well resolved, but the westward jets are more intense, so they advect the low oxygen concentrations more to the west, but then you don't have this counteracting effect at depth in the high resolution runs. Okay, so in summary, westward jets, more intense at the surface, are well represented in both simulations, and the lack of robust intermediate jets in the low resolution run causes a deformation of the OMZ, and these robust intermediate eastward jets emerge in the 3-kilometer run. They're important oxygen supply to the OMZs and may be modulating their westward extent. So we may need to monitor these jets if we're worried about the expansion of the OMZs. So within the OMZs, near the coast, the high resolution also helps to represent the boundary current system. So the redistribution of oxygen, particularly at depth, might be also important. And that's also another advantage of having high resolution near the coast, but that's something that's been taken care of by recent modeling efforts that have high resolution on the shelves and at the surface, but low resolution elsewhere, which may be a problem for the zonal jets. And of course, the correct representation of zonal jets is key for reliable long-term forecasts of ocean deoxygenation. So more details may be found in the publication here. Thank you for your attention.
Paulo, and we have time for a couple of questions. Let's see. We're going to try to hear from people we haven't heard of before. I'm going to go to the back.
Yeah, thanks. Very interesting talk. By eye, you could comfortably resolve the zonal jets at a 1/10 of a degree model.
Biology. Is it? Sorry?
So is there anything you could suggest we could do to the coarser resolution model?
To parameterize them?
Well, or just to improve the representation in terms of the numerics? Because in terms of grid cells across the jets, you have several, so
right.
They are resolvable, but is there something that, from a numerical point of view, that could improve their representation?
Well, I think we need to, well, I don't know well, I'm not a CFD guy.
Okay.
But if we could have less viscous model at low resolution, and somehow that would be made magically, that could be a way, because I think if you look at the distribution of the zonal jets, even in the low resolution one, they're there. They're represented. So it's just a matter of, and they seem to be at the right location. They seem to be at the right spacing. And I started to calculate the Rhine scale here, but then some zonal jets guys, girls and guys, they told me, okay, don't do this now because the theory is changing. But they're here, and they're more or less at the right spatial dimension. The question is, if we had a less viscous model at 10 kilometers, would these jets be more realistic? Maybe.
Okay.
Can you come up with a numerical scheme that does that?
Well, I guess I ask because tenth of a degree may be hopeful in terms of future climate models, whereas 3 kilometers is kind of
yeah. I mean, I could do this because it's in the Atlantic, and also, of course, I don't resolve. For example, Law talked today about the hydrological cycle in the North Atlantic. I go all the way to 27. So I don't resolve the whole basin.
Yeah, and we have a quick follow-up.
So to follow on Jason's comment, Paulo, how about your time averaging, right? So the jets are really emerge as an artifact of the temporal averaging of whatever you're averaging,
well,
right?
an artifact of the temporal averaging. I'm not sure. You don't see them in snapshots, that's for sure. If you look at monthly averages, you're going to see mesoscale variability that dominates that. You start to see the jets after at least a year.
That's right.
Average.
But how about
I do a kind of there's a Kurschitzer and Kung. I did that, and I cite this on this paper.
Yeah, but there's also an older paper we did with Maximenko and Wei Ping, right, back in God knows when.
Probably
long time ago,
also,
right?
Yeah.
And there was an even lower resolution. There was an even lower resolution model for the whole Pacific, where we first started observing these jets, right? And the conversation at the time was whether this is an averaging of eddies, right?
Yes.
So,
if it's an average of eddies, that's a good point. Wouldn't you see eastward and westward velocities at the same intensity? Right? Or I don't know, because I thought about this.
Anyway, so it's a conversation about so to Jason's point, I'm wondering whether if you were to take a 30-year average, whether this pattern would emerge differently.
Yeah, I reached my
and I think
limit.
one last question.
Just to curiosity as a modeler, I was surprised to see such a short spin-up in your simulation, just 7 years. I mean, did you apply any specific criteria to say, okay, I can stop the spin-up here, I can take the...
Yeah, I didn't start from rest. I started from SODA initial conditions. So SODA is a lower resolution model, but it's already spun up.
Okay.
So it's 9 years starting from SODA conditions.
Okay, I have just another curiosity, but maybe I missed the points in your presentation. But when you move from, let's say, low to high resolution, did you maintain the same number of vertical levels in your model?
Yeah, everything's the same.
Did you expect if you change the number of vertical level, the simulation on this jet could improve somehow or not? At least on the vertical direction.
Yeah. Well, I'm not sure because maybe because ROMs you can increase the resolution where you want it, so maybe there may be an improvement if you have more layers at the intermediate depth. So that might be a way, but then you start to get into
you have some vertical derivative in your balance. So I suppose that changing maybe the number of vertical level, I mean improving also the vertical resolution, probably could improve somehow the estimation of the different terms with the vertical derivatives.
Could be, yeah.
Thank you.
All right, so before I get in trouble with the other co-chairs, I just want to thank Paulo again for a really nice talk and all the other speakers. And please come back after lunch. We have 2 more speakers that we're excited to see. So, and feel free to ask more questions during lunch. Good. Okay, so we're going to head right back into our last talks for the session. And thanks very much for everyone who came back. Our first talk in the last session of this session is by Paulo Coelho from the National Institute of Fisheries and Marine Research. And we'll hear about stratification and oxygen conditions along the West African continental shelf during the last 3 decades. Welcome.
Okay, good afternoon. My name is Paulo Coelho. I come from of Angola, Africa. My presentation will talk about the evolution, the stratification and oxygen condition along the West Africa continent, shale during the last 3 decades. This work is the collaboration in this institute, the fisheries, the Côte d'Ivoire, Mauritania, and Senegal, and the Institute Marine Research in the Bergen, Norway. This is the work is the supposed the project, Nancy project. This is the data and the method. This is along the coast of Angola. This is the red point is the station. 1985, 1989, in 2019, in 2023. This is the data, data source, data selection. The station group is the vertical stability, the fixed level, and the research the question, and the using the software, KeyCast database, and manage R records and the oceanography data analysis. My presentation have two parts. The first part is the change, the dissolved oxygen concentration between the 1980 and the 2020 in Angola, in the North Africa, in the coast ocean. In the top, this is the South Africa. This is the Angola, is there. This figure shows the expanded of the oxygen minimum zone along the coast. This is the scale, this is the minimum oxygen. And the bolt, this is the Northeast Africa, and the zone minimum the oxygen in this region after Cabo Verde. This is the map, the station, this Angola, this is the Northeast Africa. This is the old Nancy, 1976 and 1993. This map. This is the Neo Nancy in 2022. This figure shows in this period, this is the small region, small oxygen region. And 2017, 2022, this is the oxygen region expanded off along the coast. This is maybe, no, this is 10 degree. In this map, 26 and 10 degrees. This is expanded along the coast. In the next slide, I show the statistics these regions in the red. We studied the standard level in the 3 deeps, 2000, this deep, this. We show in this deep the zona minimum oxygen in Angola is found into 300 meters. 300 meters. This is the average dropping at the 0.50 milliliter per decade. The P smaller anyway, another test. This is Northwest Africa. The zone minimum oxygen this is below the 400 meter. In compiling Angola is 3. This is 1960, 1998, 2009, 2022. Statistically, this region the same standard level. We showed the oxygen minimum in the Northwest Africa in the 400 meter. This is the p-values. The smaller is the 0.5. This is the significant, statistically significant result in conclusion. In the second part, we changed the water column stability and between the 99, the 2020, and the Angola, North Africa coast. This is Angola, and in Angola there are the 2 ecosystems. The 12 degrees for this the Angola Benguela front, in the 12 degrees for here is tropical region. This tropical region is set to very increase stratification, this region, in comparing this region. Those 12 degrees did separate both regions. And this figure, which very increasing the stratification in this zone, the tropical region. This is another zone. This is the Northwest Africa. This is this is Angola. In this figure, we show the increase of the stability, stratification, in decrease, but depth not show the same, not same result about stratification. These figures show because the stratification to depend the period of the warm period and the cold period. This is a warm period. This is a cold period. This is a warm period. This figure is the Northwest Africa. It's very certification in the Senegal. Senegal is 16. Certification is small in this figure, but in Senegal is more increase in certification. Stability, this is a reasonable internal variability. But in this case, in the 2015, the home period, the stratification is low, and 22 certification is more. This result not conclusive. In some recent climatology study of decrease in the oxygen in Angola, reducing the resource, the habitat for fish. The oxygen, the zone minimum oxygen in Angola, located in the 303 meters. The p-value is these values. Of Northwest Africa, to find the oxygen minimum zone in the 400 meters, which is statistically significant. In Angola, stratification is high in the tropical region, in the north of Angola. In the week in the Angola-Benguela front, below the 12 degree. This changes the water column stability in Angola, 11 degree is great. This is statistically significant. North Africa of the Senegal sides, the subface density increase. In the of maximum depth, the region of Angola present is statistically significant result. Confirm the conclusion on the ROC 2020. And the northwest zone, the result of maximum depth is not conclusive. This is my presentation. Thank you.
Thank you very much, Paulo. We have time for one quick question. And if nobody has a question, I have a quick question, Paulo. Nice talk. Do you see any relationship between the changes in stratification versus changes in oxygen? And a follow-up is, do you see the impact of natural variability where there are changes in Atlantic El Nino, or I'm not familiar with the Atlantic, that might be driving some of the oxygen changes?
No, not use the Atlantic El Nino. No. Mike, please.
That's right. It's, if I was to say, it's, there are two events there in Angola. There is Benguela El Nino and Atlantic El Nino. There are two different things. Atlantic El Nino affects Angola, and Benguela El Nino is more towards Angola-Benguela front. It actually happens in Angola and Tamil. But the point is that actually we don't have that good resolution with oxygen data, because we're also struggling, there's a big long program and fishery program, so it's a quality of work. So here we just show in bold statistics. So this is ongoing work on actually, to increase the resolution. Then we will be able to link this to interannual variability. For now, let's say this all, multi-year, 3-4 years boxes of the work. That's why it's an overall no proper trend computation.
Sounds good. Great. Thanks again, Paulo, for the wonderful synthesis. And next, we're going to hear from Sam Ditkovsky. Did I get it right? Yeah?
You got it.
From Princeton, and he'll be sharing some research on ventilation of the Indian Ocean, and how it can shed light on global oxygen dynamics under climate change.
Thanks so much, and happy to be closing out such a great session. Thanks to all the conveners. So I'll be talking about the future of oxygen in the Indian Ocean, and maybe what that can tell us about ocean ventilation as a whole. So let's start with a global picture of ocean ventilation. Here I'm showing historical and projected oxygen in CMIP6 models for what they call the subsurface, 100 to 600. And in general, we see this pattern where well-ventilated regions tend to deoxygenate, and poorly ventilated regions tend to oxygenate, albeit weakly. And as a quick note, here from Ditkovsky et al., they stipple regions of certainty across models. When I show my own figures, I switch this convention. I'll be stippling regions of uncertainty. So just a heads up. So to understand this phenomenon, this pattern that we're seeing, as Laura talked a little bit about earlier, we have this conceptual framework from a 2007 paper by Nanadesikan et al. That distinguishes between one conceptual model of ventilation, which is an advective pipe, where it's a single source, and if transport along that pipe decreases, then ventilation and oxygen supply decreases. Alternatively, in places like the ocean shadow zones, where we have oxygen minimum zones, the ocean acts more like a mixing network of many sources that slowly mix together, where ventilation is sensitive to the relative sources, the relative strength of these many sources. And the conventional wisdom is that as ocean circulation weakens with warming, the contribution of deep waters in these mixing networks declines, and we get we tend to favor more oxygenated upper ocean waters, and so we see this weak oxygenization trend across the tropics. So we have these two opposing views of ocean circulation and ocean ventilation. And in a recent paper that I co-authored, led by Julius Piasecki at Columbia, we looked at the Pacific Ocean OMZ, and we basically tracked this response, these two regimes, from this advective pipe-like response to warming to this mixing network-like response, where we see deoxygenation in well-ventilated or marginally well-ventilated regions, and then oxygenation in the really poorly ventilated regions. So this framework does a good job of explaining the Pacific, but how does it apply or fail in the Indian Ocean? So why study oxygen in the Indian Ocean? For one, it's the world's second largest oxygen minimum zone, and it has a very unique set of thermocline ventilation pathways, including marginal sea outflows from the Persian Gulf and the Red Sea into the Arabian Sea, and also the Indonesian throughflow, or ITF, is a direct tropical conduit between the Pacific Ocean and the Indian Ocean. It's also a home to a third of the world's population and rapidly growing, and is where the largest cities are projected to be by the end of the 21st century. And it's a population that relies heavily on marine resources. So for the rest of the talk, I'll be addressing the question of, in the Indian Ocean, why do we see increased ventilation where pathways weaken and a decrease in ventilation where they remain steady? So I'll outline this paradox, I'll show the results, I'll solve it, and explore how this sort of fits into our overall understanding of ventilation dynamics. So let's begin. For this work, I'm using a set of ESMs from CMIP6, and I'll be showing the ensemble mean, which does a decent job of recreating dissolved oxygen in the Indian Ocean compared to a climatology from World Ocean Atlas. And I'll be focusing on thermocline depths of 100 to 1,000 meters. And in the sections that I show, they relate to the map at 65 east, like this. I'll also be showing these contours of hypoxic waters at 60 micromoles per kilogram and low oxygen waters at 150 which act as basically a habitat boundary or a commonly cited habitat boundary for higher trophic species. And that's just to keep you oriented to the gradient in oxygen and the oxygen minimum zone in the region. So what we see in the trends is this heterogeneous pattern across the thermocline depths. And this is under a high emission scenario for the 21st century. So we see deoxygenation in the southeastern basin, oxygenation in the tropics around the south equatorial current, and then deoxygenation in the Arabian Sea. And my goal in this work is basically to explain why we see this pattern. And so the first step in doing this is to convince you that it is actually driven by ventilation and not other processes such as thermal processes or changes in biology. So we've seen this decomposition before in this session, and I'll be looking at this non-thermal term of AOU, and then also at water mass age, which is a direct indicator of changes in the physics. So in the interest of time, maybe I'll put them all up at the same time. So we see this pattern in the oxygen trends, and that's recreated when we just isolate the AOU. So we can be pretty sure that this trend is non-thermal rather than thermal. And looking at the age, which is the physics, changes in the physics only, we still see this same pattern, where younger waters match up with where we see more oxygen, and older waters where we see less oxygen. So overall, we can be pretty confident that it is indeed ventilation changes that's driving this pattern. So how does this then compare to the transport pathways that are supplying oxygen to the region? In the southern Indian Ocean, the transport through both the ITF and the southern pathway are decreasing. So here I'm showing volume transport anomalies from the historical period over the 21st century for both of these pathways, and we can see they're steadily declining with warming. So this makes sense with what we see in the southeastern basin. Less oxygen supply leads to deoxygenation, but maybe we're a little bit confused about what's going on in the south equatorial current. And looking again now at what's happening in the Arabian Sea. So one of the main oxygen supplies here are from the marginal sea outflows, and we can see that the transport anomalies through both of those pathways are holding steady throughout the time period. So this does not directly explain why we see deoxygenation in that part of the basin. So that is the paradox. Now let's try to solve it. So how can there be more oxygen, more ventilation in the south equatorial current where we see the supply pathways weaken? So even though we see both individual supply pathways weaken, and they weaken about by the same magnitude, the ratio between them, which is what I'm plotting here, is increasing throughout the 21st century. So this is the ratio of the southern pathway waters, which are more oxygenated than the ITF waters in the denominator. So we're starting to favor these more oxygenated waters from the southern gyre. And to demonstrate this shift in water masses between these southern waters and the ITF waters, I solve a mixing model using optimum multi-parameter analysis with temperature, salinity, and oxygen. So I select a potential density layer that captures this trend in oxygen pattern that we're interested in. And I'm looking at changes between some historical mean and a future mean for the distribution of ITF waters and southern pathway waters. And what we see, clear as day, is in this region, in the south equatorial current, we're reducing our contribution of ITF waters in favor of these more oxygenated southern pathway waters. And that decreases about 50%. So we're declining our contribution of ITF waters by about 50%. Similarly, we can apply the same method to the Arabian Sea, where the source waters in this case are Persian Gulf water, Red Sea water, and then the ambient Arabian Sea water, which is basically the core of the oxygen minimum zone water there. And what we see is that even though transport out of the marginal seas is holding steady in these models, we see a marked decrease in the contribution of Persian Gulf waters, which are a really important source of oxygen in the region because since the Persian Gulf is so shallow, the waters tend to stay at saturation and inject that saturated water right into the thermocline. So I'm not going to go through all the details, but the explanation for this is that this is consistent with a shoaling of the Persian Gulf outflow plume as the Gulf waters warm. So the plume basically shoals into the surface layer and no longer ventilates the thermocline. And this interpretation is heavily motivated by a study by Lashkar et al. That find a similar result in a high-resolution regional model. So to close things out, I'll just tie this back into this original framework that we talked about for ocean ventilation. So we started with these two conceptual models of the advective pipe and the mixing network, where for a single source, if ocean ventilation weakens, then oxygen supply must decrease. But this isn't true when you have this mixing network of these many sources slowly mixing together. And what our case study in the South Equatorial Current shows us is that you don't actually need these shadow zones to get this effect. 2 advective sources is sufficient. And so this is kind of the first documented case of this phenomenon within a highly advective region of the ocean. And then looking at the marginal sea outflows, we have this idea of a moving pipe. So even if transport along an advective pathway, the strength remains steady, there can still be an effect from a movement of that pathway itself in depth. So I'll leave this up as a summary slide, and I'm happy to take any questions.
All right, we got time for a few questions.
Marek Ostrowski, Institute of Marine Research here in Bergen. One of the hatchet regions that you showed was actually Bay of Bengal, where actually oxygen concentration is 0. Any conclusions? Any thoughts? What's happening in that region?
So you're saying here?
Yeah.
Yeah. Well, so one thing is, so this is only at this cuts off the first 100 meters. I think you might see very different trends in the upper 100 meters because there's that really strong salinity barrier there that will basically cut off the surface from a lot of these effects. I think also since, as I showed, a lot of the changes in oxygen are forced by these changes in the large-scale ventilation pathways, the Bay of Bengal is largely cut off from these pathways, and really in the thermocline is the only advective pathway there is an indirect exchange with the Arabian Sea. So it's possible that you would see a more delayed effect if you ran the simulation for longer, as the Arabian Sea waters started to transfer more and more into the Bay of Bengal.
I would say it's seasonal. I would have thought there is some ventilation related to southwest monsoon when you have this current actually flowing towards Sri Lanka and the formation of an eddy. So there is some seasonal mechanism. I won't say there's ventilation. Definitely. There is one, but it's seasonal.
Oh, yeah. I mean, this analysis glosses over a lot of the seasonal dynamics, which are dominant in the region, definitely. But thanks.
Andreas?
Yeah, thanks a lot. Very exciting. And you briefly, very quickly ruled out biology, which I tend to agree, but still the Arabian Sea might be a region where biology can be very important, and it might be correlated with age. So based on these maps, on patterns, I am not quite sure if there's better justification for ruling out biology.
So there is this age trend here, and I guess since it's so close to the surface, you won't expect such a marked change in age because the ambient waters wouldn't be so old to begin with. I agree that there could be a strong reinforcement from biology.
But age will be correlated to nutrients, and they may affect biology.
Well, so I guess the other thing here is it does seem like this age trend is correlated with changes from the Persian Gulf and not from the upwelling system. So I guess both could be a nutrient source, but maybe the upwelling system would be a stronger feedback in that regard.
And that concludes it for our session, Ocean Deoxygenation. I would like, on behalf of the conveners, I'd like to say a big thank you to all the presenters and everyone who attended. I think we've had an exciting session and that we've learned a lot about various different aspects of ocean oxygen. I would like to thank the co-conveners of this session as well for their hard work in putting this exciting session together, and please do continue the conversation after this session. Two other events I'd like to advertise is the poster session, so please come by and check out all the posters in the afternoon session on ocean deoxygenation. And then we also have an early career ocean professionals event tomorrow. So if you're an early career person, do come by. And then there's a hike afterwards that starts at 5:30.
If you're interested in hiking up Nguyen and doing some mentorship on the way, and we'll be meeting outside right in front of the lobby at 5:40 tomorrow. So if you'd like to stretch your legs and walk up Nguyen and do some mentoring on the way, please join us.
All right. And with that, thank you so much, everyone. We really appreciate you coming.